Thanks a lot everyone for joining us for this session on scaling Venmo application for growth with zero database downtime. Before we get going with the topic, let me first introduce myself. Hi, my name is Kushal. I'm a tech lead database engineer at Venmo. I have 8+ years of experience working on relational as well as NoSQL databases. I have been presenting at Percona Live in past as well. Last year I had a presentation at Venmo process for Aurora upgrade, as well as I will be having another talk tomorrow on Venmo's use of Proxy SQL for failover. Puneeth, if you want to introduce yourself.
Hello everyone, my name is Puneeth. I work as a senior software engineer at Melavoyraja. I have 4+ years of experience working on performance and scalability of our application, as well as have experience working on developing and managing Python-based applications on Kubernetes. Let's take a quick overview of Venmo. We're a rapidly growing payments company with uh, over 83 million active users. We have a social feed where users can share their payment activity with friends and family. Social feed drives more user engagement in our app. Our total payment volume increased by 44% year over year. Our app, our app has multiple features for both consumers and businesses to make and receive payments. A few of them are instant transfers, where a user can instantly move their money from Venmo balance to their user to their bank account. A credit card view in our application acts as a co-pilot for everything you do with credit card. Small and medium businesses can set up their business profile accounts and start accepting payments from Venmo users instantly. Other options such as paying with Venmo online or in store with QR codes are also.
Let's go through what we are going to cover in today's topic. First of all, we'll provide a high-level overview of the current architecture of Venmo. Current, I mean, what was the architecture at the start of 2021. We'll talk about some challenges that we are facing with that architecture, and because of that, how our application stack evolved throughout 2021, and what other challenges that it brought up. And we'll talk about some of the solutions we explored on resolving those challenges. And then we'll talk about the solutions that we decided to implement, and we'll also talk about our implementation approach for rolling out the solution. Then we'll cover where we are now, how things went in our implementation, and what kind of issues we resolved, and where do we stand now. Last but not least, we'll talk about what next we are planning to do to further continue our growth. Not wasting any more time, let's get going with the talk. Just a very high level architecture overview at the start of 2021. Looking at high level, like many of you might have similar looking stack. At Venmo, we use Kubernetes for hosting our application. As you can see, there is a namespace called application which has multiple, which hosts multiple application endpoints. So any request coming through those endpoints gets routed to this particular namespace. As you can see, there are multiple endpoints with this particular namespace is kind of like one of it. We do have some other namespaces and some other services as well, apart from this particular namespace. And then, as you see, there is a database layer where we have Amazon Aurora, Amazon DocumentDB, and some other data stores. For the interest of this talk, we'll be concentrating on Amazon Aurora and Amazon DocumentDB on the database side. And on the application side, these application namespaces will be our point of concentration. As you see, there are multiple endpoints part of this particular namespace. So if one of the endpoint start having some performances, start observing some latency for whatever reason, the issue quickly cascades into other endpoints which are part of this namespace. And we started seeing much wider impact because of that. That was one of the challenges that we are facing with this architecture, and I'll talk more how what we did to come over that particular challenge. Before we look into what we did to resolve that particular challenge, let's quickly look at how our API pod connection user look like and the connection on the database. So this particular API pod usage is just for one of the cluster and is more specific to the namespace that we were talking about in the previous slide. We do have multiple other clusters for HA, and they have a similar number of ports running for that particular namespace. All the connections on the right are the total connections across this particular namespace, as well as including the connections coming from other namespaces, but there's not much change in connection usage because of the other namespace. So for the interest of talk, we'll be limiting to discuss about the pod usage on for the particular namespace and overall connection usage, because most changes in the connections are happening because of this particular namespace and that we are talking here. As you can see, from January to May, it's very minor increase every month in our pod usage, and that's mostly because of adding of new features, growth, and some other factors. And similarly, you can see there's minor increase in connections, both on Aurora and DocumentDB because of that. Let's see, as you see, in May, there's a big spike in connections on the pod usage, and similarly, there is an increase in connection usage because of that. The spike in pod is because of that's when we started separating some of the endpoints that are part of that namespace, which is kind of a monolith, into some namespace into its own separate namespace. Let's see how things look like once we started migrating those endpoints into a different namespaces. This is how the architecture looked like. It kind of start off as blue end of HN time frame in 2021. As you can see, like a couple of endpoints from application namespace are now moved into identity namespace. And this kind of they just start moving things out into identity into different namespaces, but this kind of act as an first step towards breaking down monolith into microservice-based architecture. As it's still a lot more work to separate out and avoid all the dependencies between the two endpoints. So this kind of start moving to namespace and then work on removing dependency one after the other before we completely move that into its own microservice. And as we start moving endpoints out to different namespaces, this started helping us to avoid the cascading effect I mentioned earlier. If, for example, if one of the endpoint or identity names will start having issue, this will not have much of an impact to the other endpoints on the application namespace that we used to have in the past. So this service was very important for stability of the platform as well as for our customers. Let's have a slightly deeper look into how things look like within the namespace. So it's kind of same, but inside the namespace, there are multiple pods running that will kind of host your application, which will host your containers running your application. And those application pods will make connection and open database connections for both Aurora and DocumentDB as well as the data source as required. Now we can see that we added some new pods by adding the new namespace for identity, and it kind of didn't make much change on the number of pods running on the application namespace. So that means now we have more pods running, thus more application processes running, and thus we'll have more connections on our data source. And we didn't just stop by after creating identity namespace, right? We continued with separating more and more endpoints out of application namespace into other namespaces. While after we reach some stage, we start also reducing the pods that we are running on application namespace. But if we do a total math on number of pods that we are running, there are continuously increasing as we won't be able to use the same number of pods that we are adding to the other namespaces. Because you need to have some buffer in terms of capacity on respective namespaces, and thus overall we were running more pods compared to before. And this was providing the required stability to the platform. Let's look at how things look like in terms of the API pods that we are running our cluster, and as well as how things look like with the connection usage because of that. As you can see, the connections, the API pods are continuously going up linearly, and so is the connections. So from May, that's when we started separating the namespaces, and till September is like continuous increase. On top of that, just to point out that in mid-July, August timeframe, we did start looking into options of managing connections, because we knew once we continue the route of separating names endpoints into different namespaces, this could be a challenge. While we are still in the initial phase of research of what can be done, in August and September timeframe, introduced a bug. And because of that bug, there was a 3x increase in throughput for one of the endpoints. And that's just added more volatile. Because of that particular namespace had to scale further and add more number of pods to serve that traffic of increasing throughput. And thus we increased the connections even further. Right. So the priority that we have for working on managing the connections just went up. It was more aggressively tackle now. As you can see, the connection usage was very close to the limit of 30K on DocumentDB and 16K limit on Aurora. So we're getting very close to that, and we need to start working on the solution for that as a more high priority than before. Yeah, we did, but started working on solving the bug so that the connection numbers start going down, and there's some other optimization while we were working on other things. Let's not talk about some scalability challenges that we ran into because of various reasons that we talked before. Right? The one that I mentioned, like ranging to the connection limit for both Aurora and DocumentDB. What brings that is that for any event, high velocity event that we may have down the line in the year, towards the end of the year, actually event is nothing but something like Black Friday for e-commerce companies. We also have certain days where we have comparatively high traffic, and we need to scale our platform accordingly, and thus we'll be creating more connections. So because of how we were, this might be a challenge for scaling things, for managing those kind of high velocity events. As well as we have to kind of stop decoupling more endpoints, and we cannot continue to scale and bring more and more stability to our platform by doing those decouplings. As well as we are working on separating things into its own microservice for stability to convert the application stack into its own microservice, and that will be similar to decoupling of endpoints, and that could add more connections, and that will also add to the challenges that we are facing. Now let's talk about some of the solutions we explored to overcome these challenges. One quickest way will be roll back the endpoint separation for managing database connections, so that, like, as we had good enough room before we start breaking down the endpoints into separate namespaces, we can go back there. But that won't be the right thing to do in terms of stability on the platform, as well as not the right thing to do for our customers, because having stability means better performance for our customers. The second option that we're thinking about was having connection pooling on the application side, which we didn't have before. Adding the connection pooling might not be as easy as sounds like, especially the way our current application was, how our current was set up. It would have required architecture change and other changes that would have been required to even implement connection pooling, and quite a lot of some of the application might not be able to do it as quickly as we would like to do it. Keeping that option open, we continue to explore other options, what can be done to reduce connections. The was to expedite microservice migration, not just separating the application stack side of things, but also decoupling the data. And that could have moved some of the workload from the clusters that are being used part of the monolith into its own microservice, and thus could have helped reduce some connections. But some of these initiatives were already worked upon as a high priority with very aggressive timeline, so there was not much scope to exploit further without adding any more risk. And the other option that we think about was adding a proxy layer for doing connection multiplexing. Basically, just add a proxy layer in between application and database, and that can help match connections in between. And that's what we kind of decided to go with for the interest of time and the best available approach in terms of having the less amount of risk compared to other options. Let's first talk about the proxy solutions that we explored for Aurora MySQL. There are two relevant solutions available for Aurora MySQL and which are being used widely in the industry. One of them is Proxy SQL, and as we are using Aurora and our infrastructure is on AWS, we also have an option of using RDS proxy. Just keep in mind the primary requirement for us currently is connection multiplexing. We did consider other factors when comparing the two options and some of the use cases that we had while deciding which option to go with. Proxy SQL is open source and has been widely used. There's a community support available for that, and that really helps in terms of finding options or finding solutions to any issues that we may run into. It also provides support of routing traffic based on access pattern, and currently we didn't have any such requirements, but it's kind of nice to have a feature like that in case if we need in future. Inter-cluster failover, that was one of the use cases that we do have at times, like if we have to do an Aurora upgrade or we have to do any changes that cannot be done in place on the current cluster and needs to be done on a new by creating a new cluster and then failing over to that cluster. Although this is not a primary requirement, but we do have some use cases around this. We'll talk more in detail about this during our talk tomorrow, where we'll talk about how we use Proxy SQL for failover. With Proxy SQL, there are workarounds available for handling custom endpoints, just in case if you are using Aurora and separating your traffic using custom endpoints based on the use cases. Based on the workload for workload of separating traffic and making better use of buffer caches. Though as Proxy SQL is open source and something that you need to manage yourself, there's an operational overhead for managing, maintaining Proxy SQL. Also, you need to build a lot of automations around that to do day-to-day operations, do maintenance, and as well as like figure out a way of seamlessly adding a node to the Proxy SQL cluster, removing a node, doing patching on Proxy SQL, and various other things that you may encounter while running any stack. Now let's talk about RDS proxy. It's a managed service provided by AWS. Being AWS managed service, it kind of integrates well with Secret Manager. That's kind of one of the security requirement. Kind of helps meet one of the security requirements that we have. Obviously, there are other ways to meet that requirement with the Proxy SQL. It's easy to integrate with RDS proxy comparatively. To RDS proxy, it doesn't have any support for intercluster failover, as well as even being an AWS managed service doesn't support custom endpoints of Aurora for separating traffic based on your workload. The advantage with RDS proxy is that most of majority of the operational work is taken care by AWS as being a managed service. They takes care of doing the patching, replacing a node, adding a new node, and whatever else is required. Comparing the benefits between the two, you can see that in terms of feature-wise, Proxy SQL has good features that, and some of the it also meets some of our requirement in terms of use cases that we have from time to time. Though our primary requirement was connection multiplexing, which was well served by both the proxy options, and not being fully ready with doing maintenance work on Proxy SQL in an automated and seamless manner, we decided to go with RDS proxy to solve our primary requirement, especially for the interest of time and in which we need to roll out the proxy solution while doing all the other automations would have taken some time, and that's something we decided to continue to work as we go. Let's talk some more in more detail about RDS proxy. As I mentioned, the managed service. So when you spin up resources for RDS proxy, you don't have to provide any number of nodes you need for proxy. All of that is taken care by AWS, and you can charge based on the number of requests you do via RDS proxy. Once you create RDS proxy for any of your Aurora cluster, what AWS does is it will check the instance type that you're using for Aurora cluster, and depending on that, they estimate the amount of traffic that you will be serving on those based on that instance type, like how much capacity you must be serving, and then using that capacity numbers, they kind of create the number of proxy nodes behind the scene. You don't have to provide any config parameters or anything that you want to configure on the proxy layer. All those settings will be imported from your Aurora cluster. There are very few parameters that you will have to tune and tweak and adjust as required. One of them is the max connection percentage that can help control the number of connections you want RDS proxy to use to make connection to databases. Other advantage of using any proxy layer is it can help reduce your failover downtime, especially like when you are failing over within the cluster. And when as you know, like on Aurora, whenever you do a failover within the cluster, it restores all the node, not just the primary node or one particular node to restore all the node in the cluster. And with RDS proxy, what it does is anything in the flight will definitely get error, but it will stop sending any more traffic as soon as it detects that the nodes are not available on the Aurora cluster. It will hold any new request from client in the queue and wait until Aurora cluster is available. As soon as the cluster is available, it will start sending traffic to RDS proxy. Until then, it will queue things on the proxy here. Yeah, for some duration of time, that you will definitely see some latency on the available side. But obviously, it's better than having errors. Though the percentage of time that it will reduce in terms of failover and the amount of errors that you decrease in errors you may see also depends on the timeout that you have on your application side, as well as the more latency timeout parameter value that you have set on RDS proxy. If your request is taking 30 seconds to restart, but your latency timeout is 50 seconds, then you will see some of your query will start getting errors because you reached the low latency timeout. Low latency is nothing but the time latency or disk it takes to serve a database connection to a client request. Now let's talk about the implementation approach that we took while for rolling out RDS proxy. Yeah, as you can see, like there are two namespaces. We definitely have a few other namespaces, but just for example, like so let's say there are two namespaces, application namespace and the identity namespace. As you see, the identity namespace is connecting to RDS proxy, while application namespace is connecting directly to Aurora cluster. We kind of started to roll out gradually instead of big bang. Just in case if you run into any issue, we can reduce the faster use of the and reduce the risk by rolling out small and slowly, and also keep learning while we are rolling out, and not get by surprise by rolling out everything to RDS proxy. So continue to learn. This kind of helps us to get to a safer state in terms of connection usage on the cluster. By rolling out few namespaces, we had enough room in terms of number of connections available on Aurora cluster, and kind of also provided time to continue to evolve in terms of the processes and other things that we had in terms of using RDS proxy. Let's look at some of the lessons we learned while implementing and rolling out RDS proxy. While we were testing things in non-production environment, started similar to in production, like when in production, we are just kind of going through the exercise of verifying your runbook that you're going to use in production. We started with one namespace, finding one namespace to RDS proxy. That particular namespace in non-production was creating about 225 to 50 connections. Initially, we set RDS proxy with 5% with our max connection setting on our cluster is 16 KB max around value. So RDS proxy has a capacity can open up to 800 connections with fast percentage of max percentage setting, and thus it can and we didn't see any performance impact because of when we did the testing with that setting. Now, as we mentioned that connection multiplexing was our primary requirement, so we wanted to test out how connection multiplexing happens using RDS proxy and how good it is. So we decided to reduce the connection we allow to RDS proxy to below the number of connections we are opening from the client. So with 16K of max connection limit we have decided to reduce it to 1%, which allow 160 connections and a total of 225 connections. So there will be some sort of connection multiplexing happening, and we wanted to see how things behaves. Surprisingly, we started having performance impact as we started doing performance tests with their settings. After debugging further, like how many connection flux is opening, and we only found that using the application user, we only have a handful of connections and not much lot. So we work with AWS and figure out that the issue that we were running into was that um, certain number of connections were being reserved by RDS proxy for various tasks that RDS proxy needs to do, like health check, monitoring, and various other things, which only had left out a small subset of connections out of 150 of allowed limit. So there were not enough connections available for data for serving client traffic. This is something I mean you might not run into if you're not doing testing with a very small subset of connections, but just something to keep in mind if we are testing that and may run into that issue. It was good that we kind of figured out what's going on, so we increased the number of pods we are running on that namespace, and that will increase the number of connections that we are opening from client, and this we were able to increase the percentage that we have set up on RDS proxy and continued from there. And we were successfully able to test and things work fine as expected. One other thing to keep in mind is because of whenever you run into borrow latency spike, proxy will do the right thing and consider that we don't have enough database connections available, and thus for a client to use, it will open more database connections so that any new request coming in will have a free database connection available. But the issue that we ran into was that whenever we do have a spike, instead of gradually opening more database connection, RDS proxy will open a bulk number of connections in most cases, like all the way up to the max allowed limit that you have set for RDS proxy. So that's something to keep in mind. Again, we kind of ran into this issue more when we were running only subset of connections, like few namespaces via RDS proxy, and there's our percentage that we were using was less, and with more number of proxy instances running in the background, each proxy instance only had subset of connections, a very small number of connections per proxy instance, and that could be one of the factors that we did observe low latency at times, mainly on deployment, as a lot of connections will come in chunk to RDS proxy, and that's where it will request more database connections. So we didn't observe any performance impact because of that on overall in terms of our platform. So it was fine to continue running subset of namespaces to start with, and then gradually build on top of that. And once we started rolling out more namespaces, this issue started getting very less frequent as we had more traffic. Last but not the least, yeah, we did observe some latency by adding additional layer in between. So from end-to-end application perspective, there was about 2 to 3 milliseconds of increase in latency if you look at the latency numbers on APM. We have also similar numbers when testing with proxy SQL as well. So in those cases, it doesn't make difference in terms of using proxy SQL or RDS proxy. Next, we will talk about proxy options for Mongo as well as AWS DocumentDB.
Let's take a look at how we solve for the connection scaling problem for MongoDB, DocumentDB. Some of the options that we explored for MongoDB, DocumentDB, The first one is MongoDB Proxy. It's an open source library written in JavaScript. It opens one connection per replica set, and it uh, doesn't offer connection multiplexing as a feature. And it was not being maintained for the past 7+ years. The second one that we explored is Aurora. It's an open source project from Facebook. It does offer connection multiplexing, but after further investigation, this project has been archived and no longer being maintained for the last 5+ years. The third one that we looked at is Mongo Proxy. It's an open source library as well, and it supports connection multiplexing, and it's written in Golang. It's not being actively maintained for the past 6+ years. We thought of using this library internally within Venmo by forking it and adding necessary features that we need. This is before we ran into Mongobetween. Mongobetween is open source library from Coinbase. It's currently actively being maintained. It's written on Golang. It does offer connection multiplexing, also have good support for observability and other things. So in the 4 options, we decided to go ahead with Mongobetween, and we started testing Mongobetween on our platform. So let's take a quick overview of Mongobetween. As I said, it's written in Golang. It uses Golang MongoDB driver internally to achieve connection multiplexing. At the startup, Mongobetween opens a small pool of connections to DocumentDB, and it has an option to configure the max number of connections that it can open to DocumentDB. It opens new connections based upon the load that it receives. Also, it manages a small amount of state for supporting cursor-based operations. It is designed as a sidecar. Coinbase ran into a similar problem when they were doing their deployments. They saw this thing called connection storms on their Mongo database. That's when they came up with this solution, and then they open sourced it. It has a really good integration with StatsD client. We have integrated with our observability application on our end, which is very easy. So as we tested MongoDB in our platform, we tested 2 different approaches. Let's take a look at difference between each approach and some advantages and disadvantages for each approach. The first one is a service-based approach. So when I say service-based approach, it's Mongobetween as a service. It's similar to what we saw with RDS proxy or proxy SQL. So if you see the diagram below, Mongobetween is deployed on individual pods, and all these group of Mongobetween pods are behind a service, which is nothing but a load balancer. An application that wants to connect to Mongobetween connects to through the Mongobetween. An application that wants to query DocumentDB connects to Mongobetween pod through this load balancer, and Mongobetween pod internally opens a connection and relays that query to DocumentDB. So some of the advantages are, number one, it's cost effective. Reason being, we run a set amount of Mongobetween pods for supporting all different applications on our platform. The second one is management of these service is simple. Reason being, it's centralized and we can update any changes to all the Mongobetween pods. And the third one is it's the most efficient way of achieving connection multiplexing. Reason being, a connection could be used by any application on our platform without any issues on a given Mongobetween pod. One major disadvantage with this approach that we discovered was it lacks authentication. What that means is Mongobetween, when it starts up with the credentials configured on the Mongobetween pod. If a connection is already created on Mongobetween pod, anything outside, like any application pod, can connect to Mongobetween service and then query DocumentDB without providing any credentials. So that is a major disadvantage. So let's take a look at the second approach, which is a sidecar. It is exactly same as what Coinbase has done on their end, according to their blog. What a sidecar is, we run Mongobetween as a container inside the application pod. So if you see in the diagram below, we run a Mongobetween container and application container. So when application container wants to query DocumentDB, it connects to Mongobetween container. Mongobetween container relays that query by opening a connection to DocumentDB. And Mongobetween container does the connection multiplexing for all the incoming requests that it receives from the application container. So few advantages are it is isolated to failures. What that means is Mongobetween container, if it has any issues, it only is impacted for that specific pod and not across the board. And the authentication is strictly restricted within the pod. So only application container can connect to Mongobetween and then route a query DocumentDB. Nothing outside of that can connect to Mongobetween container. And the connection multiplexing is not fully extensively used. We are not taking full advantage of connection multiplexing compared to the service-based approach. Reason being, the connection multiplexing is applied to only incoming requests from the application container. So anything that comes from application container, if will be limited. There will be limited number of connections coming from application container. So that is one minor disadvantage. Let's take a look at our implementation on how we added Mongobetween on our platform and how we rolled it out. So as you look at this diagram, we see two namespaces here, but in reality, we have multiple namespaces running in our platform. So the way we rolled out is we approach one namespace at a time, which is a gradual approach. And for a given namespace, we added Mongobetween container to run along with the application container. In that step, only container spin-up was being done. Application container continues to connect to DocumentDB directly without connecting through Mongobetween container. Once we confirm that Mongobetween container is up and running without any issues, we have a feature flag in the application container when that feature flag is turned on, it will start routing the connections and the queries to Mongobetween container, which is on the pod. And also at the same time, we are closing connection, if any connection is open, directly to DocumentDB. Reason for that is to keep the total number of connections more or less the same on DocumentDB. And then once we run the feature flag to 100% and we observe, and if everything looks good, we move on to the next namespace, rolling out same changes onto the next namespace. Some of the lessons that we learned as we migrated or applied Mongobetween as a sidecar in our application are, number one, we saw a minor increase of latency, query latency with Mongobetween in place. When I say query latency, it comes from Mongobetween because we have an extra hop that we're taking, and it is few milliseconds from what we have noticed in our tests and what we have seen in our production. The second issue that we ran into is when we tested Mongobetween, it didn't have support for read preference. So any query that was being sent with the read preference or secondary preferred or secondary was not being honored. It was being sent to the primary of DocumentDB. So for this, we work with AWS DocumentDB team to get this addressed. Thanks to DocumentDB team, they have opened a PR on MongoDB repo for adding support for this. We have subsequently rolled out this change on our end on our platform. So let's take a look at where we are now. So as you saw initially in the presentation during the first half of the year, we were running a single namespace where everything was going to every endpoint was living in a single namespace. As we moved across and did the namespace separation, we currently have multiple namespaces where different endpoints are routed to different namespaces. And we have RDS proxy running in front of Aurora, and all of the applications connect to RDS proxy and leverage this connection multiplexing. Similarly, for DocumentDB, we have Mongobetween sidecar container running on the application parts to connect to DocumentDB. Let's take a look at a current state of things with regards to connections and pod counts on our platform. So during the start of the year, we had a gradual increase in the number of pods as we started doing the namespace separation, as Kushal mentioned. During the September-October timeframe, where we had the bug of this extra amount of traffic, that's when we almost hit closer to maximum number of connections on both Aurora and DocumentDB. As we work and fix that bug, we had a gradual decrease of connections and the number of pods during the September and October timeframe. But also during that timeframe, we were working on this proxy solutions. And if you see in the graph around November or December timeframe, we started rolling out solutions for Aurora and DocumentDB. one namespace at a time. And as you see, towards the end of last year, we were trending up with regards to the number of pods that we are running. That's due to reasons one is namespace separation as well as organic growth in our application, in our plan. As the number of pods were trending up, if you see during the December and currently to today, the number of connections started trending down and pretty much stabilized in the March and April timeframe. That's when we almost rolled out MongoDB, Mongobetween, and RDS Proxy in most of our workloads. What next? We continue to implement RDS Proxy on the rest of our Aurora clusters in our platform. Also, we are investing some time to add authentication to the Mongobetween proxy so that we can leverage or implement service-based approach. One major driver behind it is the cost. We save cost with this approach. Since running sidecar needs more compute on our Kubernetes clusters. And the third one is we are working towards gradually moving our services or our endpoints to a more of a microservice-based architecture, which is our final end goal where we want it to be. As I talk about microservice architecture, we have a talk coming up tomorrow, which talks about how we use Proxy SQL to move to a microservice-based architecture for one application. And we are hiring, feel free to take a look at this staff database engineer position. We have a lot of challenging and exciting problems to solve. Please come join us. Thank you very much, everyone, for attending this talk. We can take any questions now.